So we've covered that. And this is just a different configuration of the F-test that we looked at last week. And so it's for that F where we get 107.203. Where does that number come from? Why does it matter? What does it mean? It comes from taking sums of squares regression and dividing it by number of independent variables and sums of squares residual and dividing it by n minus k minus 1. And then that's going to give us an F value. And then we could do that little exercise, and then we're going to get 107.92. Then we could do that little exercise like we did last week, and we could use the F table with degrees of freedom equal to 6 and 1,127, sorry. We could do the hypothesis test, right? In our case, we have the good fortune of having SPSS that gives us that significance level. So we don't have to use the F table, we just need to interpret that significance level. And so that is where that F value comes from. And it really is important that if you get to this stage and if this value, if you can't reject the null hypothesis that that r square is not significantly different than 0, then you really can't go on. You have to stop right there, because you've said that your variance explained does not deviate significantly from 0. You've not explained any meaningful amount of variation in the dependent variable, so consequently, it just doesn't make sense then to go look at the independent variables because they don't explain anything. And in fact, all of the t-tests, for the most part, there could be some weirdness that happens in some cases, but my guess is in most cases, if this is not significant, all of your t-tests are also not going to be significant. Sometimes there can be a little bit of disconnect there, but that would just be the rare case. And so just remember it. And my hope is, well, let me say this. If you do your analysis for the homework number 2, and if this is not significant, send me an email, because we need to come up with some different data to use, because it wouldn't be fair for you just to stop right here and say, oh, I don't have to do anything more because my analysis wasn't significant, right? So I didn't put that note in the homework assignment, but it's on the recording now. So make sure that if you have that, and I can find you some other data that you might be able to work with, or you might be able to mix up your data. But I think most everybody the data that I looked at, I just don't think it's going to be a problem. But in case it is, you might want to do a little bit of exploration on your own if it's not significant, and maybe just find a variable that will help, or a couple of variables that will help. And so here is the coefficients, and this is usually, you look at the r square. How large is the r square? Is it significantly different than 0? Yes. Then you have the justification to look at this table. And in our case, we do, and we can look at a couple things here. How would we interpret this 0.638, the B coefficient for how often they pray? what's the interpretation of that coefficient? What does the 0.638 tell us?
That's all I got.
That's good. So for every word, that's
like
good.
1 unit, then there's an increase of 20.
How often is in religious services?
There's pieces there that seem right, but I don't think
Putting the puzzle together.
the sum of the parts don't equal.
The change in
Marissa's going to give it to us.
I was going to say for every increase in 1 unit of church attendance, the
No.
no.
But close.
Wrong.
Every 1 unit of recorded how often prayer goes up, then how often our attendance religious service goes up.
Right.
Oh, I know.
So for so for every 1 unit change in how often they pray, we would expect that the increase in religious service attendance would increase by 0.638. And if you look at the equation, you should be able to sort of come to that same conclusion, right? This is y predicted is equal to minus 0.255 plus 0.638 times how often a particular person prays, plus 0.994 times that same person, their strength of affiliation, right? And this is in the same form as the equation that we looked at earlier, just that in this case we list out all of our variables. And so if you think about it, if we increase prayer by 1, how much would we expect the predicted value to go up? Well, it's going to go up 0.638, and so that is the interpretation. And your challenge really is to look at this data, other studies that you read that report regression analyses, your homework, and look at enough of these B coefficients so you don't even have to think about the interpretation. It's not, is it the independent variable, the dependent variable, what order they go in? It needs to be sort of an intuitive understanding that you can bring to bear on this. And I think if you look at enough data, that will probably pretty quickly become the case. And so, if everything was 0, somebody have a question?
How important is it to say that keeping all the other items constant?
Yeah, that's really important to say that we would expect as prayer increases, for every 1 unit increase in prayer, we'd expect a 0.638 increase in religious service attendance, controlling for or holding constant the other variables in the analysis. Yeah, and so that add-on is really important. So, what is the predicted value if everything were 0? If all of the independent variables are equal to 0, what's the predicted value going to be? What's that?
minus 2.55.
Right, and if we look at our data, we don't have any negative numbers for the dependent variable, and so the constant quickly becomes not a particularly useful metric to understand. And the reason why, in our case, why this is negative, because in some cases 0 isn't even a possibility. And so we don't have anybody, age of 0, our population is all 18 and above, they're all adults, and so 0 is outside of the range of our data, and so there's just, when you have those kinds of situations, then the constant becomes some number that isn't interpretable, and in most cases doesn't add a lot of value for the hypotheses that we're testing. And if you really did want to interpret the constant, you could just make sure that 0 was a meaningful value for all of your data. And remember we talked about z-scores? Standardized scores would be one way that you could do that, where a z-score of 0 is the mean. And that probably a better way to do it, instead of taking the z-score. And the z-score is, to create the z, remember it's x minus x bar, right? Divided by standard deviation. That's the formula for z. And probably if I were to do this and I really wanted to have this be meaningful, I probably, instead of dividing by the standard deviation, I would just center the data and do x minus x bar. So the mean is now 0, but the standard deviation stays the same. And then this number would be constant, or this number would be meaningful. The constant would be meaningful, and essentially the interpretation would be when everything is set to the mean 0. This was what the predicted value. This is what the predicted value for religious service attendance would be. And so, anybody remember how to calculate the t value? How do we get this column?
Oh, the b divided by the standard error of b.
Yeah, just like you did with kurtosis and skewness, it's dividing some coefficient, in this case a b coefficient as opposed to a skew coefficient, or skewness variable. We're just 0.638 divided by 0.048 is going to be equal to 13.151. And then we could get a t-table out. We could get a t-table out, and the degrees of freedom is going to be greater than 120, and most t-tables only go up to 120, and then it's infinity. And we'd be able to then get this significance level. But of course, we don't need to do that because SPSS gives that for us. And so, sort of interesting, if we look at the analysis, what sort of strikes, what's not significant? Age is not, in the overall, and by itself, I thought age, the 0 order correlation. Does anybody remember the correlation?
0.1.
I don't remember what it was, but in this case, controlling for the other features in the analysis, age doesn't matter. Sort of surprising. I think about, well, I won't go there, but I would have thought age would have mattered. Does income matter?
Life after death is life.
Life after death doesn't matter either, does it? That's sort of interesting too. Once we control for how much somebody prays and how their strength of affiliation, perhaps then whether they believe in life after death, which might bode well for Amanda's idea that we really probably should measure life after death in something other than a dichotomy. It's probably more than just that binary that would be worth understanding. And so those are the two that are not significant, right? Life after death and age, right? Is that right? Everything else was significant? And we know that from this column, right? We'll talk about these two columns next week.
That's just a quick question. It's only measuring it linearly though, right?
What's that?
It's only measuring it on a linear from this one.
That's right.
So that could be significant.
Right, and I'm gonna do that before all said and done, maybe not today, but we're gonna test that. The competing hypotheses that it's either linear, it's but inverted U or U, and see which if either of those it is, and that'll be a pretty straightforward analysis to do. So here I say this is your time to get your calculator out and your phone to do. This is what you'll have to do for the homework, where I'm asking you to calculate 5. I'm asking you to calculate 5. Is that the number right? 5 predicted values, and then calculate the residual. So here's the data. I actually used SPSS to give you the predicted value and the residual. So you're not going to use those. You need to actually use these to do the calculation. And I tell you to do 1, 2, 6, 9, and 14. So you can do those 5 cases. It'll probably take you 5 minutes to do the first, and then a minute to do each of the ones after that, because once you get the first one down, you'll be good. And so calculate the predicted value and the residual just to make sure you can match it up close enough with these, and then we'll see if there's anything of interest. Anybody not have a calculator or a phone? If you have your computer, you could do it in Excel pretty quickly. So we should be able to use, just if anybody's sort of questioning what they should be doing, you should be able to use this formula here, right, and plug in those values, and then just do that multiplication and addition to come up with the predicted y, right? Did everybody get at least one of them to work out? Anybody not get through one of them? I won't ask that very long. We'll just take a few more minutes, and you may not get through all 5 of them. But I think you get the hang of it, and you'll do the same with your data. So we'll just take a few more minutes, and then I want to talk about a few of these. So one of the things that we'll talk about next week is that, and if you didn't get through all 5 of them, I'm assuming that you have some understanding of what the sort of tedious calculation is, and you'll be able to do the same with your data. If not, I'm happy to help when we get done here. One of the things we'll talk about next week is the residual. If you had to explain to your best friend who's not in this class what a residual is, how would you explain? What is the residual? How would you explain to your mom what the residual is?
The difference between the predicted value and the actual value.
Yeah, and they might, right. I think that's about as simple as it could get. And so if we look at residuals that are large in absolute terms, what does that tell us?
That the prediction was not very good.
Right. And so if we look at the largest residual we have there, again, in absolute terms, it's case number 1, right?
Right, the 3 point.
Right. And so this person was predicted to go to church with a 6, which a 6 would be 0, 1, 2, 3, 4, 5, 6. Nearly every week is what his prediction was, or in that range. And he actually, what he reported is less than once a year is what he or she, I don't know, this person reported that they go less than once a year. And so his predicted value was high, but his actual value was low. What do you think made the predicted value so high? If we look across his data.
Prayer.
Or her data. What is it?
Prayer being so high.
Yeah, so prayer is 5, and 5 for prayer is 0, 1, 2, 3, 4, 5, several times a day. So this person reported that they pray several times a day. And the pattern with other respondents is when they say that, they are attending religious service more frequently. This person said that, and they attend less than once a year, and that's, I don't know what that's probably they do believe in life after death, and their strength of affiliation. That's sort of a little bit wonky too, isn't it? So they are
They were just a graduate
0,
student
1.
just trying to survive instead of praying a lot.
Yeah.
So they're only 25.
So their strength of affiliation is not very strong, is what a 3 would represent, um, and there's somewhat of a disconnect between it and well, maybe not a disconnect between it and their actual dependent variables. So the thing, I think probably the thing that's driving the would be they're so high on this variable, higher than most others, and so that's what drives their prediction up to be nearly 6. And so what we'll find is we can learn a lot about our data by looking at extreme residuals, and we don't get rid of extreme residuals in most cases, but they help us to understand our data, and they help us to understand what issues we might be having with prediction. And in some cases, we might need to get rid of them because we might identify some pattern there that is just so extreme that they need to probably remove from the data. But in most cases, if you sort of follow the logic that we have talked about all semester, where first you're going to sort of clean up your act in terms of your data, and you're going to check for outliers, and you're going to check for multivariate outliers. And if you do all of that, you'll probably have less to do in terms of analyzing your residuals and some of the other techniques that we'll look at in terms of diagnosing just how confident you can be or should be in your regression analysis. So just in terms of the homework number 2, everybody's comfortable with that, being able to do that? And so we have B, which is what we've talked about so far, right? And then we also have beta. And so we want to talk just a little bit about beta, or a little bit more. The strength of the B's are not comparable if your independent variables are measured on different scales. So you have some things between 0 and 7, and some things between 1 and 9, and some things between 1 and 100. They're all on different scales, and that interpretation is based on one level of increase in a particular independent variable will lead to a certain amount of change in a dependent variable. And if one of them is measured on a 1 to 100 scale, and another one is measured on a dichotomy, clearly you shouldn't be comparing those, the B's. But beta weights are comparable with probably a lot of caution. I don't say a lot, but I just say with caution. And generally range between 1 or minus 1 and 1. But they can fall outside that range in certain situations, as indicated there. The formula for beta is pretty straightforward. Beta for independent variable J is just the B for independent variable J divided by, or times the standard deviation for independent variable J divided by the standard deviation for the dependent variable. So you'd first just do this division and multiply it by the B, and you're going to get a value that will generally range between minus 1 and 1. If we just calculate the beta for prey, in our case, I would just get what's our list-wise standard deviation for the independent variable prey, and it's 1.48652. What's our list-wise standard deviation for the dependent variable? And then you could just do the math, and you get 0.3497, and 0.3, whoops, going the wrong way, 0.3497 should match should match for 3497. How often they pray, so it rounds to 3.50. So that's the calculation, and you can easily do this for. You don't have to do this for all of the beta weights, but when asked in the homework to do a calculation, you certainly can calculate this for well, you can do it for all four if you wanted to, or how many independent variables you had. But I would expect that you would do it for at least a couple, and then just make sure that you're using your listwise n. It can't be total n. If you're deleting some people out because of missing data, don't calculate. You have to take that missing data into consideration when you grab the standard deviations, or you can have some problems. And you'll get this if you ask for the descriptive statistics in the dialog box. It'll give you the list-wise standard deviation for and mean for all of your variables. So you'll have everything you need to make that calculation. So one strategy that some, for various reasons, you could just standardize all your data, and then your B will be equal to your beta. So you could just do the standardized score for your dependent variable and all of your independent variables, and then your B's will be equal to your beta. And there'd be a few situations where that will be useful, and if we get a chance to talk about when that might be useful, we can do that in the coming weeks. And so I think one sort of cautionary note, at least from my perspective, I always prefer B over beta. I just don't have a lot of confidence that beta would be stable from sample to sample, and so I prefer and really expect researchers to report. I don't care if you give me beta, but if you don't give me just beta, you can give me B, and I'll be happy with that because that's my preference. You can give me both, I'll be happy with that, but don't just give me beta. And you'll find, I see it in communications some, maybe in older publications more than sort of current state of the art, where people will report just beta. And then if you go to econ or political science, nobody ever reports a beta. It's just not of interest. And it really is because the B there's an interpretation there that once you understand it, that is intuitive, and people that look at this for a living, like a lot of scientists do, they just want B. And then beta can be unstable in some cases, given that we're using the standard deviations from a dependent and an independent variable for its calculation. And so, and it's always a little bit, even in our case, if we go back here and look at our betas, what we could look at, and the two strongest relationships would be between how often they pray and recoded strength of affiliation, right? The 0.364 beta is 0.364 and beta of 0.350, right? But to say that the strength of affiliation in a meaningful way, in a significant way, in a statistically significant way, is greater than 0.350, we don't have that information from this table. We can't make those kinds of claims. It may be, it may not be, right? The difference between 0.350 and 0.364 may be meaningful or statistically significant, and may not. So I think you always have to be cautious. There are some tests that you could do if you really thought you had that kind of hypothesis, that you wanted to compare, two independent variables to see which one has a stronger relationship after controlling for several other features. There'd be some ways to do that, but we can't do that from this. You can just sort of get some understanding of how we might rank how we might rank the influence of the independent variable on our, or variables on our dependent variable. So does that make sense? So that's my advice is just to report both. If you think you need to report beta, just please also report B. And so we've talked a fair amount about dummy variables. Do we have any dummy variables? Let me look. Are any of these dummy variables? Yeah, life after death is, right? It's just a dichotomy, right? It's either yes or no. And so we consider that's just a dichotomous variable. How would we interpret the 0.082? What's the interpretation of this? Given that the understanding that we have about interpretation of the other these, how would we interpret that? Is it significant? In this case, it's not even significant, right? So say it was significant. What's the interpretation? William, you look like you.
I'm just trying to think how do you know if I'm assuming 1 equals yes and 2 equals no? Or
Yeah, in this case, one is equal to 1 is equal to belief in life after death. 0 is not believing in life after death.
Okay. Then you would say if you believe in life after death, then you will go up 0.82 on how often you attend religious service.
Compared to somebody who doesn't believe in life after death. And so it's the difference between it's the difference on the dependent variable between believing in life after death and not believing in life after death after controlling for all of the other variables in the analysis.
So if it was a negative, then would that mean that not believing in life after death means that would increase?
That means that if it would be
If it was a negative, because
since it's positive, it means that a person who believes, and it's not significant, so we have to we have to keep that frame of reference in mind. But in this case, it means that the person who believes in life after death attends religious service attendance more, 0.082, than somebody who doesn't. And if it was negative, it would be the person who believes in life after death attends religious service less than the person who doesn't believe in this case, it's essentially it's 0. We can't. The 0.82 doesn't vary significantly from 0, and so essentially it's 0. Or it doesn't vary. It's not 0. It doesn't vary significantly from 0. That's an important distinction. I'm not saying it's 0. It just doesn't vary significantly from 0, right? To say it's 0 is one thing, but to say it doesn't vary significantly from 0 is a different thing, and that distinction can be really important.
Would it be okay to say that it's the prediction on how often one goes it's 82 times more likely for those who believe in life after death than others?
Not 82. What did you say? Because of the 0.82? No, it's on the same metric as your dependent variable, and our dependent variable was 0 to 8. And so it's 0.082 on that scale, which in no way would be it's a small movement in terms of percent. Does that make sense? Other questions? And so just a little bit more about dummy variables. Think back to week 1 when we talked about dummy variables. And we have this implied group, because if we have a nominal variable that has k groups, we're going to create k minus 1 dummy variables, right? And the group that's left out is what we call the implied group. And that there's some thinking has to take place when you determine, well, what group should I leave out? It probably isn't just the first group or the last group. It might be, but in most cases, there's probably some intuition that would be helpful in your interpretation. So if we had an experimental study where we had people that were in stimulus condition number 1, got some stimulus, and stimulus condition number 2, got a different stimulus, and then a control condition. So we had a categorical, that'd be one categorical variable that indicates were they in group stimulus 1, were they in stimulus 2, or were they in the control, right? So it's just nominal. And we probably would, in SPSS, stimulus 1 might be 1, stimulus 2 might be 2, and control might be 3. But you could do it some other way too. It could be 0, 1, 2, 3, doesn't matter. The numbers don't matter because it's a categorical variable. But for our purposes, for this example, let's say we did do 1, 2, and 3. We only need 2 new variables, right? And if I tried to do all 3 of them, and I use that and put that into SPSS, it's gonna remove one of them for me because it can't do some. It's like trying to divide by 0. It doesn't know what to do. It can't do that. You can't divide by 0. And so it just, the machine has to get rid of one of the variables. And so we always have to do k minus 1. And in this case, it might make sense, for me anyway, in this scenario, to do the reference group would be the control group. So I want to compare, or the implied group is going to be the control group. So I want to compare stimulus number 1 with the control, and I want to compare stimulus number 2 with the control group. And so what I'm going to do is I'm going to create 2 dummy variables, one called variable 1, and if stimulus number 1, I'm going to make it 1, else 0, and another variable that's going to be called variable number 2, and if it's the stimulus 2 condition, I'm going to make it number 1, else 0. So I'd have 2 columns of data. If there's 0 on both, what does that mean?
Control.
If they're 1 on both, what does that mean? You screwed something up, right? We can't have, they wouldn't be 1 on both, right? They can't be, if you did something wrong, if they're 1 on both. But if they're 0 on both, that means in this case, that's the implied group. That's the group that is in the, that's the control condition. So here's some data, not made up data, but data from an election a long time ago, where it was this kind of experiment where I had 66 people who were in what I call a Bush condition or stimulus 1, and that's what this 66 is telling me here. And then I have 62 people who were in a Gore condition, and then I had 62 people who got to watch ESPN instead of watching TV commercials about candidates. And so what I have is a dependent variable, and it was that we don't really care about this dependent variable for our purposes, but it's just how close they felt to Bush on the issues. Did they feel a long distance from him, or did they feel like their issue understanding or their issue beliefs align with Bush? And so these would be our means. So the people in the Bush condition had a mean of 5.79. The people in the Gore condition, when we ask about Bush on the issues, were lower, not surprisingly so. And then the people who watched ESPN were, or whatever I had them do, were in the middle. And so this is that nominal variable where I just did descriptive statistics on it. This is the dummy coded variables that I created, one for using the vernacular on the previous screen, stimulus 1, stimulus 2, watched Bush commercials, watched Gore commercials. And we can see that I have 66 people that are coded as 1 for Bush condition, which makes sense because I have 66 people here, right? And then I have 62 people that are coded as 1 for the Gore condition, which of course matches up with this. And if I did the regression analysis, which would be pretty straightforward, we'd have the dependent variable would be the Bush issues variable. And then remember, for regression, we can't use a nominal dependent variable. So if I put that nominal variable in there with those 3 groups, SPSS wouldn't know any different, and it would actually treat it as if it were continuous. So we have to dummy code, and that's of course what we did. And the first thing we look at is does our R square vary significantly from 0? What's the answer to that question? Yes or no? Why? Tyler, you're shaking your head. What is less than 0.05?
R squared.
The R square is, yeah, but that isn't the test for R square, right? Or what test are we looking at? If we want to know whether this varies significantly from 0, we're looking at this F test over here. So if that's what you're talking about, you're talking about this? Yeah. So it's this significance level is less than 0.05, which says that this varies. It's a meaningful, we're explaining a meaningful some amount greater than 0. Small, medium, or large?
Small.
Small is what?
Small and medium, 0.01.
And medium is what?
0.09.
So it's closer to small than large, or medium, right? So we'd say smallish or whatever.
Schmedium.
But it, huh?
Schmedium.
Yeah, that you could try that in your dissertation and see what you can say. And so here's the important part. So this is significant. So we sort of get the green light to look at our coefficients. And the interpretation here is, this is the key. And so when Bush condition and Gore condition are equal to 0, what is the condition that's being represented? And what would be the predicted value for the control? If both of these are 0, 5.715, and somebody go back and look on the previous screen, what is the mean for the control condition on the dependent variable? Should be 5.715. Huh? 5.72, so it rounds to that. So when these two are equal to 0, then the condition that's being represented would be the control condition, and the predicted value for the control condition would be 5.712. And if we were representing, if we wanted to predict what the mean would be for the Bush condition, what would we do? It's going to be 5.715, and then what? Plus
0.079 times a value for the.
and what's that value going to be? It's going to be 1, right?
Well, right.
Yeah, because the Bush condition is 1 or 0, right?
Right.
And so if we wanted to predict for the Bush condition, it's going to be 5.715 plus 0.079. Somebody do that on the calculator. And that should be equal to the mean for the Bush condition that we had on the previous slide. Just check to make sure it's right. And then if we wanted to predict for the Gore condition, of course, if if Gore is equal to 1, Bush has to be equal to 0, right? And Gore is equal to 1, so it's just 5.715 plus a negative 6.92 times 1, and do that math, and that will be equal to the mean for the Gore condition. And so the way that we would interpret this at the end of the day is that the Bush condition wasn't significant when compared to, there's no significant difference between the Bush condition and the control, but the Gore condition was significantly lower than the control condition. So when the people watched the Gore political ads that I had them watch, Al Gore's political ads, they felt a lot more distant from George Bush on the issues. George W. Bush, not H.W. George W. Bush. They felt more distant to him on the issues. But that wasn't the case when they watched the Bush ads. When they watched the Bush ads, they didn't feel any closer to Bush than people who watched, I think, I don't remember what I had them do, but say it was ESPN, sit there and watch ESPN commercials for a few minutes. So that's how you could do, what other tests could we, if we didn't want to do regression, what other tests would we do with this data? What other tests would you do?
No.
Yeah, it would just be a one-way ANOVA, right, where you have one independent variable and 3 groups, and you could compare, you could do plan comparisons and compare the means of the 2 conditions with the control condition, if that's what you're hypothesizing. And then another look that really isn't too much different than the analysis that we did on religious service attendance, but just sort of drives home the point. So in this case, the dependent variable, and those of you that didn't know this, I studied political comm when I was in the department, so for better or for worse, most of my examples will come from well, I don't pull on, this is probably one of just a couple that we'll look at. So in this case, the dependent variable was one that I studied a fair amount, was the issue salience. So we asked voters, what issues are most important to them. And some voters say, I only care about this thing. Don't give a rip about anything else. And then other voters might say these 2 things, and some voters might have 10 things, and some voters. So issue salience is how many things are top of mind, how many issues are salient to them. And so the question is what are the predictors of salience? What are the people who have more things salient to them, more issues that are important to them? It's sort of an interesting and there, you can probably draw on some democratic theory and as to why that's important. But how would we interpret? And by the way, this is how I would code your dichotomies. And so in this case, biological sex, male or female, I wouldn't call it sex. Not that I have a problem with the word sex, but it just doesn't really tell me anything. In this case, I call it female, and female is coded 1, male is coded 0. And it just gives me, then you don't even have to tell me what's coded high and what's coded low. I know that this is female, female is coded 1. I know this Democrat's coded 1. This is did they get political information from the internet, and just a dichotomy, yes or no. And so that is code 1. So my preference would be, and it's something that people that do data, and if you read journal articles from experienced data analysts, they would never put the word sex or biological sex here. They would always just tell you which one it is, because it just makes interpretation that much easier. So what is the interpretation of the 0.129 for female? How would we interpret that? Is it significant? It's not significant. Is it close? Not really. It's not even really close. But say that, let's just interpret it as if it were, what would the interpretation be? Yeah, so females have 0.129. The minimum was 0, the maximum was 10, the mean was 1.6 issues that people had. Females had 0.129 more issues that were salient, but that doesn't vary significantly from 0, and so essentially we'd say that there's not a statistical difference between males and females, controlling for all of the other features in the analysis. What's something that is, so the very last one, they were asked if this is American National Election Survey data. They were asked if they watched the debate, and sometimes they asked, did you watch part of the debate, half of the debate, the whole debate? This is, did they watch the whole debate? And these are the presidential debates. I don't remember what year. And that one is significant. And so the interpretation there, as you would probably theorize, that somebody who watched the debate had 0.28 more issues that were salient to them than somebody who didn't watch the debate, controlling for all of the other features in the analysis. And 0.28 doesn't seem like very much on a scale from 0 to 10, but it's greater than we expect to get by chance, right? It's a meaningful amount, but it probably, if we were just to look at effect sizes, the effect size probably would be quite small, or would surely be in the small range. So that's just a little bit about dummy coded variables. Questions about the homework? Take a look at homework number 2. Tell me if I haven't covered something that you think we need to cover.
I just have a question. In the output, do you always say list-wise in, or sometimes just say in? You can tell.
It's there's a preference in regression for list-wise. There isn't. It's just a list-wise by default. You'd have to write syntax to do it.
Well, I saw the preference where you could change it, but it doesn't. It just says in. It doesn't say list-wise in. So I know
But you have the preference set to list-wise, then it is list-wise. And so you can do list-wise or yeah, and so yeah, and it'll be the list-wise. Other questions?
Yeah.
So homework number 2 due next week before class. Yes. Happy to help if you have questions before then. Have a good rest of your week. Enjoy the warm weather.
Recording?
Okay.